I'm Anjana. Hello. Hopefully you can see my slides now. And I am here to talk to you about immutable data structures for functional programming in JavaScript. First, just a couple of words about me. I am engineering, learning, and development lead at a company called Mapbox. Mapbox, in case you don't know us, we are a location data company. We make a series of platforms to help you, developers, include really great customized interactive maps, guidance, location-based experiences of all sorts in your applications. You can check us out at mapbox.com. And I also want to tell you a couple of words about a few programming and tech communities that I'm really lucky to be a member of, an alumna of. One is called the Recurse Center. The Recurse Center is a programming retreat in New York City, kind of like a writer's retreat, but for coders. So it's a place you can go for 6 weeks or 3 months and just work on getting better at programming, whatever that means to you. It's a really fabulous environment. Check it out at recurse.com. And another organization that I'm lucky to have participated in is called Outreachy. Outreachy is a fabulous initiative that aims to try to get more women and members of underrepresented groups involved in open source by offering paid remote internships at organizations like Mozilla to work on open source projects. And if you know someone who's trying to break into tech, this is a really great way for them to do it. If your company works with open source technologies and would be interested in sponsoring interns, in either case, go check out outreachy.org and read a bit more about the program. It's a really wonderful initiative. And so in addition to being a former intern at Mozilla, I'm still a Mozilla community member, and I'm a Mozilla tech speaker, which we also got a couple more of in the house. Woo! And you can find me at a lot of these kind of events around Europe and the US. So never hesitate to come up and say hello. And if you want to chat about any of these things, I am more than happy to do that if you want to find me after the talk. But I'm not really here to talk about all of those cool things. I'm here to talk about immutability. And the reason that we want to talk about immutability is because functional programming is very cool. I think functional programming rocks. Anybody agree with me? Yes. Woo! Awesome. Okay, so we're not going to talk too much about the nitty-gritty of how functional programming works. I'm going to say a few words about it, but if you want to know more, go talk to those people that just made noise after the talk, because if they like functional programming, they love talking about functional programming. So just in a nutshell, basically functional programming is the idea of looking at your program as being composed entirely out of pure functions, where a pure function is a function that all it does is take in some arguments as input, perform some kind of computation using only those inputs and looking at nothing else in your program or in the world, and then returning some kind of output as a return value. And so this means that pure functions, programming with pure functions, is programming without side effects. Side effects are anything that a function might do other than return its return value. So for example, modifying the value of some global variable, or changing something that exists outside the function, or printing something, logging something to the console. That's a side effect as well. So the idea is that we want to think about programs in the functional world as being composed of these sort of data transforming functions that just take data in and return data out, and that's it. And that means that one thing that is conspicuously absent in functional programming is mutable state. The idea that global state or even individual objects that can be changed in place, that are mutable, that's seen as dangerous, it's seen as problematic, and we're going to look at why. And so one thing that goes along with one of the reasons that functional programming rocks so hard is because immutability rocks. Having immutable data is really awesome for some reasons that we're going to see in a moment. And I would like to, for dramatic effect, talk a little bit about something else that rocks to help us understand why immutability rocks, and that's rocks. Rocks also rock. So I took the liberty of stealing a rock from outside. And I would like you all to please just consider this rock for a moment while I read you a poem, because we need more poetry at programming conferences, I think. So, nobody sits like this rock sits. You rock, rock. The rock just sits and is. You show us how to just sit here, and that's what we need. So this is a poem from the movie I Heart Huckabees. I don't know if anyone's ever seen it. Jason Schwartzman reads this poem a little bit better than I do, but that's okay. He's a professional. So why do rocks rock? And why does the rock just sitting and being, why is that what we need? The rock shows us how immutable data can be so cool. So let's imagine for a moment that we live in another world where all data is mutable. We can change it in place. This would be kind of our normal, everyday programming world. Okay, so imagine I have an array. This is a mutable array, and it's got some numbers in it. It's got a 0 and a 1. This is super boring. Why are all programming examples always named boring stuff like foo, and they just have like boring integers in them? This is silly. I think we should make it more fun and more cute and make it a zoo instead with animals. Yeah, and so in fact, we actually have a real life zoo in the audience today. We got some folks rocking out some onesies really hard. Can we take a moment and just appreciate their onesies? Do y'all want to come up for a second? Check it out, check it out. Yeah, look, real life zoo, yes, excellent. Okay. Oh, wait, Chewbacca, wait, come here. Okay, so this is my zoo over here, right? Now, in the land of mutability, if I want to change something, maybe I want to, let's see, what do I got? I got a panda there in the middle that maybe I want to replace with something a bit more exotic, like an alien. So, Panda Bear, would you mind? Thank you so much. Let's give it up for our wonderful panda. Okay, so notice, so now I've got a zoo that's a bit more exotic. It's got an alien, Chewbacca, in it, instead of the original Panda Bear. And this is cool for me because I just didn't have to change anything about the rest of my zoo. All the other animals just stayed where they were, and I just swapped out one. Right? So that's cool for me, except that I had a coworker somewhere who was working with the zoo with the panda, and Dominic was not there anymore. And they're like, what? Who moved my panda? I was counting on there being a panda there, and I had not handled the edge case of a Wookiee being in the zoo. That was not part of my plan. My code can't handle it. And so now things are broken, and what do we do? Okay, thank you so much, zoo. Let's give it up then. Again, yes, lovely. Little bonus live action in the conference talk. Okay, so I swapped out a real terrestrial animal for an alien extraterrestrial, and my coworker had a bug in their code. And this is one of the hazards of mutability. When we are changing data in place, we can change things out from under each other. I can change something out from under my coworker, or out from under a past version of myself who didn't handle that edge case in my code. And so this means we need to implement a lot of overhead, a lot of management to make sure that who is changing what when, and it happens in a safe way, and that we check that things aren't aliens before we deal with them. And that's a lot of headache. That's a lot of overhead. And invariably, we make mistakes. We trip up. We don't handle Wookiee edge cases, and then we get bugs in our code. So mutability is dangerous for these reasons. And that's why, as much as I love Professor X, I must disagree with him. We must stop mutation. It's great for the comic books, but it's not so good for our code. So let's now imagine we journey to a land of purely immutable data. So immutable data just sits and is, like the rock, which is going to sit over here for the rest of the talk. Okay, so immutable data, once I've put it there, it's not going anywhere. And in an immutable world, if I had a zoo that I created, once I've created it, I can't change it. So if I want a new zoo that has an alien in it, I would have to create a new array. I would have to insert my alien into the new array, and then copy over all of the other values, all of the other animals that I don't want to change, I don't want to update in my array. So this is cool because my coworker is now happy. Her zoo just sits and is. I didn't touch it. It's the same as it always was. And I'm happy because I now have a new version that has an alien in it. Aliens are cool. But we do still have a problem. And that is that this code, this copying that I did, it's really slow, like a turtle, because I had to go through and copy all of the values in the whole array, even though I just wanted to change one little thing. And it takes up a lot of space, like a big old whale, because I needed to allocate an entire new array, the same size as the first, again, even though I was only changing one little thing. So copying is not a really great way to deal with immutable data. It works, and we can get the benefits of immutability, of stuff just sitting and being, but it wastes time and space, so it's not efficient. So there must be a better way. And indeed, a hero comes along called persistent data structure. Yeah. Okay, you may not know why they're so cool, but you're going to in a moment. So persistent data structures are like masters of time and space. Basically, in a persistent data structure, old versions of your data, they are immutable. They just sit and are. And new versions are created efficiently. Now, before we go on and look at exactly how these work, just a note on terminology. Persistent data structures and immutable data structures, those words are sometimes used a little bit interchangeably. They're technically different things. Immutable refers to once it's created, it never changes. Persistent data structures, on the other hand, have to do with the fact that old versions hang around. And I'm not going to go into the different types of persistence here, but if you want to check that out, you can Google types of persistence and in persistent data structures and find out about partially persistent, fully persistent, et cetera, et cetera. For now, we're going to be talking about persistent immutable data structures. So for the rest of the talk, we're just going to consider that as one concept, although the technicalities are a little bit more nuanced. Okay, so persistent immutable data structures. What is their deal? What is the source of their powers? It's two very simple, beautiful things: trees and sharing. Sharing is a superpower, y'all. It's true in functional programming, and it's true in life. Let's see why. Okay, so as a regular immutable array, I had a zoo before, but we saw that if that's immutable, it's not very efficient to deal with. So if I want to make it more efficient, what I can do is turn this into a tree, which I do by splitting up my array into nodes. Now, I could split it up so that each individual value, each animal, gets its own node, but then they might be lonely, so we'll put them with a buddy. So we'll split it up into groups of nodes that are of size 2, that have 2 animals, and then what I'll do is I'll take a pair of those nodes and link them up. So I'll link up pairs with other nodes that are also of size 2, and then I'll take those linking nodes and link them up and keep going like that until I get a root node that unites the entire structure and unites all of my animals into a single structure, which will be my zoo. So now, zoo is a little bit more complex. It's got a little bit more structure, but it has the same animals. It's got the same data. And we're going to see that this structure allows us to deal with updates more efficiently. Okay, so if I want to update my zoo, and I want to put an alien in it instead of the koala or whatever that I had before, how do I do that? Well, what I need to do is look at the leaf node that contains the value that I want to update. So in this case, I have that node 0, 1 on the left-hand side that you can see there. And what I want to do is update that koala at index 1 into an alien. So I will copy that single node and create a new version that contains the alien at index 1 instead of the koala. And I do need to copy my monkey, which was already there at index 0. So I do need to do a little bit of extraneous copying, but much less, because I only had to copy 1 extra item instead of the all 7 extra items that I had to copy before. I don't need to touch any of the other nodes besides the one that contains the value that I want to update. So then what I do is I create a new intermediate node that links up the new version, the updated version of my leaf node, with whatever other node its previous version was linked to. So I basically copy that intermediate node, creating the new link, and then I keep doing that up and up until I reach a new root that reunites my new copy of that node with the updated value with the old values that I didn't change. And this is my new version. And so what I just did is I copied all of the nodes on the path from the value that I want to change, which is at a leaf node, to the root of the tree, which represents the entire structure. That's unsurprisingly called path copying. And the beauty of this structure is that I can share the majority of it between the old version and the new. And that, unsurprisingly, is called structural sharing and is really great because now I don't need to copy most of the data. I can reuse it between the old version and the updated version. So this is pretty cool because I didn't need to unnecessarily copy a bunch of values that are staying the same. Okay, so just to recap, trees and sharing are superpowers, and they allow us to turn a way of handling efficiency that was really slow and took up a lot of space, a way of handling immutability that was really inefficient, slow, and took up a lot of space, into a way of dealing with immutable data structures that's much faster. So we go from our turtle to a racehorse, and takes up a lot less space because I got to share a lot of the nodes between the trees. So from a big old whale, my program is now taking up the size of a little shrimp. Okay, you may be wondering, cool, I have this weird tree structure, but how do I get anything out of it? How do I access one of my animals if I want to look something up in my persistent data structure? And this is where it turns out that our tree that we've turned this array into actually has a secret identity. It is a tree. What? No, it's a T-R-I-E, tree, which I'm going to pronounce try, and is usually pronounced try, just to distinguish from T-R-E-E, tree. Although it could be pronounced tree, T-R-I-E, tree, because it comes from the word retrieval. And this is basically a special type of tree. A try is a type of tree that has the values in leaf nodes, and the paths from the root to the leaves represent keys with which those values are associated with. So I said that this T-R-I-E can be pronounced tree like retrieval because this is often used for doing things like retrieving values from, let's say, a dictionary type structure where maybe I want to have a dictionary of animals and each of their emoji icons is associated with the name of the animal. So what I could do is create a tree where, starting at the root, I have a branch for every possible first letter of one of the animal words in my dictionary. So I have like an A branch or B branch, etc. And then from the A node, I have a branch for each possible next letter. So since I have ant and ape in my dictionary, from A I can go to N or P. And so on and so forth until I reach the end of a word, such that if I want to look up, okay, what animal do I have at the word ape, I take that word, ape, and I break it down into letters, and I go from the root, I go to first A, then the P branch, and then E, and I end up at the emoji icon I want of my ape, my gorilla here. So this is often also called a prefix tree. Try is often called a prefix tree because you'll notice that at each level of the tree, I have a prefix of the word that ends up being associated with the leaf node. Okay, so this is cool, but we're not actually doing this. We were trying to have an array type structure where I have like indices associated, an integer associated with each animal. So how is this useful? Well, if we take our index of the animal that we want to retrieve, and we convert it to binary, then we can treat that binary number kind of like a word and retrieve our value at that index by stepping letter by letter or bit by bit through that binary word. So how that looks. Okay, I've taken our zoo tree and I've just annotated it with zeros and ones for the left branch and the right branch. We always had two branches at each node. I'm just going to call those 0 and 1. And so then we notice that at the leaf nodes, the indices are kind of like our binary words there, where we have 0 is now 0, 0, 0, and 1 is 0, 0, 1, et cetera, et cetera. So when I want to retrieve an item at a particular index, I take the index. Let's say I want to find out which animal is at index 5. or I want to grab the animal at index 5. I take the index 5 and I convert it to binary. So now it's 101. And then I step from the root of the tree to the 1 branch, and then the 0 branch, and then the 1 side, and I end up, I go 1, so the right-hand side, 0, left-hand side, 1, right-hand side. I end up at the value 101, just like I did with my ape word before. So this is the insight here. Now, if we treat these indices as binary strings, like words, then we can step through letter by letter and get to the item that we want. So what is this that we've just seen? Is it a bird? Is it a plane? No, it is a bitmapped vector trie. I don't know. Okay, this is just jargon. You don't need to worry about this, but if you really want to look this up, you could go Google that. So bitmap vector trie is just the name for this type of data structure. Bitmap because we are basically at each level, we are descending, we're looking at a particular bit in the index in binary. And a vector is the word that's often used for kind of an array-like object when we're dealing with these persistent data structures. And we'll see that that pops up in some libraries that we use later. Can somebody let me do how I'm doing on time, by the way? You'll like boo me off the stage when it's time to go. Great, okay. So let's quickly talk about time complexity while we're talking about time. With a regular immutable array, lookup is really fast. It's constant time because all I need to know is the index and boom, I go right to it. But as we saw, when I was dealing with immutable arrays and I had to copy the whole thing when I wanted to update something, that meant I had to copy everything in the array. So that's a linear time operation. So updates are really slow with regular immutable arrays. However, with my cool persistent data structures, the bitmap vector tries, both lookup and update involve going from the root down the path from the root to the leaf that I am interested in, whether it's I'm looking something up or I'm updating something. So both lookup and update end up being logarithmic in the length of the vector or the array type thing. So this is cool because we have faster updates, but this logarithmic lookup is not so amazing, especially if you had really big indices that would be really, really big binary strings. You'd have to go like through 15 different levels to get to like the 1000th element. Those take forever, right? So as your array gets bigger, the number of things you're gonna have to go through to get to the value you're interested in is still gonna grow. So that's kind of lame because this is supposed to be efficient, right? The thing is, we've been talking about this so far with a tree that has two-way branching at each point. So we have basically two options at each node. I can go left or right. But nobody said that we had to have a tree with only two-way branching. So in the trees that we've seen so far, which have two branches because they fit on slides, we have basically representing one bit of information at each level of the tree. I can only choose 0 or 1, left or right. That's only one bit of information. But we could imagine choosing a different arbitrary number of branches, where if I have a small number of branches, what I'm going to get is those deep trees that we saw before. And if I have more branches, like say 8 or 32, I would have much shallower trees. However, there's a trade-off because as the number of options at each level grows, that means I need bigger nodes to like remember the paths to all of those different options. And so as the size of those nodes grow, that means that I'm gonna have to spend more time copying. When I want to change one node, I'll have to copy over extra things. So it's really a trade-off between the depth of the tree and the size of the nodes. But people have experimented with this and found that in general, the sweet spot is 32-way branching. This is kind of hitting the nice balance point between depth and size of nodes. And that means that we have 32 options per node, 32 ways we can go. So that represents like 5 bits of information per level. So what that means is that now if I had a really long index, like this one, like 18,977, is this really long 15-digit binary number. You don't need to worry about it. Before, we would have to step through 1 digit at a time. Now we can step through in chunks of 5 digits. We can basically break off 5 bits of information at each level because we have 32 options that we can go at each level. So this means we now have a much shorter path to traverse from the root to the leaf that I'm interested in. So what this means is that, yes, okay, still we have logarithmic time lookups and updates, but the base of that logarithm is so big, 32, that even if we have something like 2 billion plus items in our array, log base 32 of like 2 billion and whatever the like largest integer that you can represent in many systems is like between 6 and 7. So that's often called effectively constant time. And this is why sometimes you read about these data structures as offering effectively constant time lookups and updates. This is what they mean. It's still logarithmic, but it's just like the base. If you choose a good one, it makes it effectively very small. So, okay. So far we've been talking about array-like objects where we have integers as indices that are associated with values, but we want to have regular kind of key value objects. We want non-integer keys. So how do we do that? Well, it's actually a really simple insight. In the land of immutability, all of your objects are immutable. So if you have keys like letters, like maybe I want a tree that associates the first letter of each animal's name with its emoji icon, like M for monkey, K for koala. Those are immutable, those strings, so I can hash them. And that means I get a number, I get some integer that represents each key. Even if that key is whatever, if it's a string or if it's some other type of immutable data, I can still hash it. And then with that number, I can just convert it to binary and descend the trie as I did before. So for example, if I want to look up which value is associated with the key G, can't read that, but I'm guessing it says 5 minutes. Okay. If I want to look up which value is associated with the key G, I just take some hash function and put G into it, and it's a really convenient hash function, this one, because it gives me 5, which is a nice small number. And then I convert that to binary, and just as before, I traverse the tree, exactly the same. Now, the numbers probably wouldn't be in order, as they conveniently are on my slides, but that's okay. It's a key value association, and we don't usually expect them to be in order, so that's all right. Okay, cool. So now I've got data structures that I can associate values with whatever keys I want, and I can get at them really quickly, much more efficiently when I want to do an update, change something, than if I were dealing with immutable, regular old, boring, non-persistent data structures. And this object version, associating keys with values, that's called a hash array mapped trie. If you want to Google something, you can Google that. It's a data structure kind of pioneered by a guy named Phil Bagwell and then implemented in languages like Clojure and Scala. And a lot of functional languages have native implementations of these data structures, which is how we are able to do functional programming efficiently, because we need immutable data to do functional programming, or it helps a lot anyway. And so these really cool data structures have helped us do more efficient functional programming. Okay, just a quick recap. Mutability gives us headaches because we have to manage who changes what. Immutability rocks because our data doesn't change, and so then we don't have to worry about it causing bugs later. Copying is inefficient, but using persistent data structures that are structured as trees, which can take advantage of structural sharing, makes that much more efficient. So I only have a couple of minutes left, so I'm just going to very quickly mention how can we use some of these data structures in our JavaScript code. Libraries! You don't have to implement this stuff. People have already done it. Don't reinvent the wheel. Use theirs. So one of the libraries that we can use for such data structures is called Immutable.js. Comes out of the Facebook kind of React ecosystem created by Lee Byron at Facebook. This is a pure kind of JavaScript-oriented implementation of these, and so using it feels a lot like using regular JavaScript. If you were to create the array-like object is called a list, or that might be the one you use. The syntax to create one is a bit weird. You do like immutable.list.of and then the stuff you want in it. And then what else is a bit strange, for my opinion, in this library is that then you have this immutable list, but you can use sort of array-like methods on it. Like you can, if you have a list called A, you can do a.push3 and push 3 onto your list of 1 and 2. However, that is not changing A. It is returning a new thing that is sort of a new version of A, which you can then capture as A2. And you can prove to yourself by checking the size that A never changed. So this feels a lot like JavaScript. There's also maps for objects, but in the interest of time, I'll just gloss over that. There's another option that I just want to show you quickly, which is a library called Mori, which is a ClojureScript port to JavaScript. It basically aims to let you allow ClojureScript's implementation of these data structures, which come from the Clojure world, from the comfort of vanilla JavaScript. So you can use some of the benefits of ClojureScript, which Lisa is going to tell us about a little bit later. So I won't say too much about ClojureScript because we have a whole talk on it. But you can access some of those cool things from regular old JavaScript. And Mori offers a list or array type object, which is called vector. But the difference between Mori and Immutable is that Mori comes from this functional programming world, the Clojure land, where we are going to only use pure functions. We're not going to use those kind of method calls, which feel a little bit more like object-oriented programming. So instead of calling a.push, I'm going to call mori.conj, which is like the Clojure function for adding something onto an array. And then I'm going to pass in the original array a as an input argument, and the new thing that I want added on to a, and that's going to return a new vector called a2. So the difference here is in like kind of the feel of using an object-oriented API with Immutable.js and a functional, very like pure function-based API with Mori. There's a couple of other differences between the two. Like, for example, Immutable.js is a little bit smaller. Mori may not be so much maintained these days. I haven't checked it in a little while, but I think it's been a couple of years since it's had any updates. But there are tons of other options there. If neither of these is floating your boat, you can Google for JavaScript persistent data structures. One you might want to look into is Seamless Immutable, which offers you the choice between the object-oriented API method call type interface and the functional API. So yeah, if you're curious about using these, check out these libraries, check out some of the references that I'm going to have at the end, and go forth, live long, and don't mutate your data. Thanks very much.